So one element replaces another. That means I have to start off with an element by itself if it's going to do the replacing, and I have to have something to replace it in. So I need a compound. So my reactants are going to be an element and a compound. And the products, well, when I replace one element with another, that means I get a new element by itself because I had one replaced, and I end up with a new compound because I've got a new positive piece. So trying to keep these straight, I like to use a dance analogy for the different types of reactions. So what do I mean by dance analogy? Well, you can think of a combination reaction, the first one, as the beginning of a dance. Before the music starts playing, you have people by themselves, elements. The music starts playing, they go out on the dance floor, they form couples, a compound. So a combination reaction is like the beginning of a dance. Things by themselves coming together, making a compound. Decomposition is the end of the dance. The couple's out on the dance floor, music stops playing, had a couple, they go their separate ways. Now you go from one piece to two pieces. That's decomposition. So decomposition is like the end of the song. Single replacement, something that shows up in ballroom dance, is that there's a couple out on the dance floor and somebody goes up and taps on the shoulder, says, mind if I cut in? So you started off with somebody by themselves and a couple. When you're done, you got somebody different by themselves and a different couple on the dance floor. That's what this is saying. Something by itself, an element, and a compound, a couple, end up with a new somebody by themselves and a new couple on the dance floor. Okay? Here's an example. Na is an element, plus potassium chloride, a compound. And the fact that it's an element plus a compound tells me it's going to be single replacement. One by themselves, a couple. So the sodium is going to cut in and take the place of potassium, which is going to kick the potassium off. So the potassium's by itself, and the sodium ends up next to chloride. That's a single replacement. Sodium replaced potassium. It took its place in the chemical. That means potassium had to end up by itself. We're okay with this? Okay. Why did sodium replace potassium? Because things that are like each other replace each other. Because fluorine, when it reacts with a compound, fluorine reacts with lithium chloride, fluorine does not replace lithium, because fluorine is not like lithium at all. Fluorine's a nonmetal, lithium's a metal. Those two can't replace each other. What fluorine replaces the other nonmetal. So fluorine replaces the chlorine, and lithium ends up next to fluorine instead of chlorine, and the chlorine ends up by itself. But chlorine can't be by itself, so I put that little 2 there. It's one of our 7 diatomic ones.
So what if it's like a metal and a compound with 2 nonmetals?
It won't happen because it doesn't have anything to replace it, and something else is going to happen.
Okay.
Yeah, so they have to be able to cut in. So metals always replace metals, non-metals always replace non-metals. Oh, does it bug you? It bugs me that this isn't balanced. Got 2 F's, so I got to put a 2 in front of LIF. That gives me 2 LIs, so I put a 2 in front of LICL. That gives me 2 CLs, which I wanted anyway. So here's the first reaction in pictures. Sodium by itself, potassium next to chlorine. Sodium kicks the potassium off. and the sodium ends up next to chlorine, and the potassium ends up by itself. Single replacement. Pretty descriptive of what happened. See how it's like cutting in at the dance? Sodium takes the place of potassium, and the potassium ends up by itself. Or, apparently fluorine's twins. So the fluorines don't take the place of the lithium, they take the place of the chlorines. And the chlorines end up by themselves. But chlorine can't be by itself, so it's Cl2. Single replacement. So metals replace metals. I had some chemicals back here I was going to use. Oops, got there. Guess I have to mix some more up. The magnesium's gone. Okay. So, magnesium. So metals replace metals, and hydrogen behaves like a metal if it's written first. Okay. So, Mg reacts with CuSO4. So here we've got a solution of copper 2 sulfate. To it, I'm going to add, I brought it over here. Where did I put them? Here's my zinc. I brought the magnesium too. Where did the magnesium go? I brought it. Oh, there it is. Okay. To that, I'm going to add some little pieces of magnesium. Stir, so those go in there. Okay. So I put some silvery magnesium in with copper 2 sulfate. Okay. What am I going to make? Well, the magnesium is going to take the place of the copper. So magnesium is going to replace the copper. So magnesium is going to end up next to SO4. I keep the 4 because sulfate's a polyatomic ion. Polyatomic ions stay together. And the Cu is going to end up by itself. Now I got to worry about subscripts. Same process. Can Cu be by itself? Yeah. Mg is 2 plus. SO4 is 2 minus, so that's the right formula. Then we have to balance. 1 Mg, 1 Mg, 1 Cu, 1 Cu, 1 SO4, 1 SO4. It's all balanced. Okay. So if I do that, if I do what that says, I should start off with a silvery metal, magnesium, and a blue solution, the copper 2 sulfate. And when it's done reacting, I should have a bunch of new metal. See the new metal floating in here that wasn't there before? And notice that it's not as blue as it was before. That over time that blue, because copper 2 is blue. Copper, the metal, is orange. Okay? So this is getting less blue because the copper 2 is coming out and turning into the solid pieces of metal. The little silvery pieces of metal that were there, the magnesium, they're disappearing. And they'll be in the solution. Okay? So making some solids that weren't there before. Single replacement.
So aqueous solution, or would that
Yeah.
be straight up liquid?
No, that would be an aqueous solution.
Okay.
Okay, so because it's still in, so it's still in. This was dissolved in water, so the sulfate was dissolved in water. So the sulfate stays dissolved in water. Okay. Now, if I had put aluminum instead of magnesium, same thing would have happened, but it would balance differently. The aluminum would chase off the copper, so aluminum would end up next to sulfate, and copper would be by itself. Then we got to decide subscripts. Does Cu get a little 2 next to it? No. Al is in group 3A, so it's 3 plus. SO4 was 2 minus. Those don't add up to 0, so I got to do the crisscross. I get Al2, SO4, 3. Hey, and we can do this. Somebody mentioned it earlier last week, but we can talk about it here. Notice how SO4 didn't change from one side to the other? So does it make sense to count it separately as S's and 4 O's? As long as the polyatomic ion stays together, you can count it as a unit, which will save you some counting. Okay? So 1 Al, 2 Als. I'm going to put 2 in front of aluminum. 1 Cu, 1 Cu, that's okay. 3 SO4s. Oh, I got to put a 3 in front of CuSO4. That gives me 3 Cus, so I put a 3 there. And then we're fixed. So counting S's and O's together as SO4s. So what happens if I put some zinc here's some zinc, some zinc metal, and to that I add some sulfuric acid. As it sits there, it starts to bubble. You see it bubbling? So it's bubbling. What are the bubbles? Let's find out. There's 2 ways to find out. One is by doing some math, and the other is by catching it. So, zinc, it's a metal. It's going to replace the positive piece there, hydrogen. So zinc is going to end up next to sulfate. And hydrogen will be by itself. So I did what the name said, single replace. Now I figure out subscripts. Does H get a little 2? Yes. SO4 is 2 minus. ZN's over here, but remember it's one of the 3 on your polyatomic ion list that says it's always a 2 plus. So 2 minus and 2 plus adds up to 0, so that's okay. Then we have to balance. 1 ZN, 1 ZN, 2 H's, 2 H's, 1 SO4, 1 SO4. That was hard. Sometimes they balance easy. Okay. But according to that balanced equation, that's hydrogen. I only know one way to check. Is it hydrogen? Yes, it's hydrogen. Okay. So it's not just letters on a piece of paper. See how much less green less blue it is now? Okay. I don't know how much of my magnesium I got left in there. Okay. So we changed colors because the copper came out of solution. We got extra little floaty bits because we see the pieces of copper. Those little floaty bits are little tiny pieces of copper, not just letters on a piece of paper. Okay. Okay. And the tricky part. Water, we're always used to writing as H2O. But another way of writing water is hydrogen hydroxide. And in single replacement reactions, you want to think of water as hydrogen hydroxide. Why? Well, hydrogen hydroxide because the metals will replace one of the hydrogens, but not both of them. So one of the hydrogens will come off water, so the metal will end up next to hydroxide, not next to oxygen. So for example, if you put sodium and water together, if they wrote water as H2O, you're going to want to rewrite it as HOH, because remember, hydrogens can come off. It's hydrogen. So sodium and water. So sodium is going to replace one of the hydrogens. I'm going to have sodium next to hydroxide. And hydrogen by itself. Can hydrogen be by itself? No, hydrogen gets a 2. Okay, so I've got one Na on both sides. That's okay. And actually, this is a little bit different balancing. I'm going to call this hydrogen hydroxide. So over there I have 2 hydrogens and 1 hydroxide. So I need to put a 2 here to get my 2 hydrogens. That gives me 2 hydroxides. So I need to put a 2 in front of sodium hydroxide. That gives me 2 NAs. So I put a 2 there. So if they write H2O in a single replacement reaction, we got to change it to HOH to see what happens with it.